So I'm going to follow the standard format that was sent to us. My name is Alain Kassab. I'm a faculty member in the Mechanical and Aerospace Engineering Department. Here is my contact information. I earned my Ph.D. degree in 1989 from University of Florida. I spent 2 years as a visiting professor with a center in West Palm Beach, a joint venture between UF and Pratt Whitney, and I've been at UCF since 1991. I've served for nearly 15 years as a graduate coordinator, and in 2016, I was tasked with developing the BME program in our department. And so I've been in that position since. In terms of teaching, I've taught a variety of standard courses in heat transfer and fluid mechanics at the undergraduate and graduate level. Currently, I'm teaching a course in modeling methods at the undergraduate level, EML 3034. This is a numerical technique course with applications in aero, heat transfer, fluid mechanics, and such, and a graduate course in computational applied biofluids. This is taught every spring. My research interests are in numerical techniques. I've been doing this for 30 plus years. In computational heat transfer and fluid flow, inverse problems, which I'll describe briefly. Coupled problems, boundary element method, an area that I've been doing quite a bit of work in the past 25 years, and meshless methods. In the past 12 years, I've taken the skill set that we developed in engineering context with applications to heat transfer, fluid flow, and such, to bioengineering, and that was spurred one of personal interests, and then a collaboration that I developed with a very distinguished surgeon at Arnold Palmer Hospital, Dr. William DeCampley, who's also a physicist. He has a dual degree in physics, astrophysics actually. So it was we had an ability to talk with each other across these disciplines in a very easy manner. So we're applying computational methods applied to single ventricle congenital heart disease, and also some issues raised by ventricular assist devices having to do with thrombus transport. So some examples of output of our research. We have a couple of books that we wrote in boundary element methods, published by Wessex Institute of Technology, and then this book which just appeared, published by ASME Press, as an introduction to boundary elements, meshless methods, and finite elements. In the BEM, you just discretize the boundary. It's based on integral equation. It's an integral equation-based approach where to solve a field problem, you just need a surface discretization, as opposed to a mesh, which appears in finite elements and finite differences. In meshless methods, you just have a point distribution where there is no particular structure there's no grid and no mesh itself, hence the name meshless methods. And these techniques have really gone through an explosive development over the past 10, 15 years, and we've been engaged in methods development. Inverse problems illustrated here. For example, if you have a subsurface cavity whose geometry you're trying to detect, that's an unknown boundary. With additional information that's gathered by temperature measurements, for example, by an infrared scanner, from that footprint, you may be able to detect the subsurface cavity. Another example would be, well, we know the geometry, but we don't know the boundary condition. It's inaccessible, and we'd like to determine what is occurring, what is the heat load, etc., and an internal boundary with additional measurements. Non-traditional way of solving problems in reverse, that's hence the name inverse problems. And I'm on the board of a journal dedicated to inverse problems, and I'm editor of a journal dedicated to both of these techniques, Elsevier journal dedicated to boundary elements and meshless methods. I've organized a lot of conferences on campus, my first in 1994, and then the latest one that I organized on engineering frontiers in pediatric and congenital heart disease was at the UCF College of Medicine. From a programmatic point of view, I've developed a minor in bioengineering in the college, and then worked with Bill Self in biomedical sciences to develop a sister minor in bioengineering for biomedical students. And we instituted the Masters in BME in 2016. That's been a very successful program, well subscribed. And I'm coordinating the Medicine Engineering double degree program with Burnett School and Biomedical Sciences in the Burnett Honors College. And I've been fortunate to mentor a very capable set of graduate students over the years. So my research then, involves numerical methods applied to solving engineering problems. In my teaching, I'd like to integrate that and get our students motivated and appreciate the power of numerical methods in engineering. And obviously, I'm applying these methods to bioengineering applications. And we've had a very close relationship between engineering and medicine over the years, and that has really accelerated and promoted my interest in migrating to that area of focus and research. So here are two examples from mechanical engineering publications on that particular subject. So the first of the projects that I'd like to just briefly highlight was sponsored by the American Heart Association, and it was our first sponsored project, which entailed dealing with what is known as the hybrid Norwood procedure, which is a first stage reconstructive surgery for hypoplastic left heart syndrome. So hypoplastic left heart syndrome is a disease that's manifested by a non-functioning left ventricle, which usually provides blood to the systemic circulation, an atrophied aorta, a non-functioning mitral valve, and an atrial septal defect. And so at birth, soon after birth, because this is not a viable circulation, reconstructive surgeries are staged in 3 stages, the first of which is a traditional Norwood. And the ultimate aim is to utilize the right ventricle as the motive power for blood flow in the body. And so the pulmonary arteries are dissected off of the pulmonary trunk, and the pulmonary trunk is utilized to form an aorta, to form a new aorta. And ultimately, through 2 other stages of surgery later on in life, in 6 and then later around 1 year old, the superior and inferior vena cava are dissected off of the atrium and connected to the pulmonary artery. And so the right ventricle pumps to the systemic circulation, and blood returns to the lungs directly through the inferior and superior vena cava. And that produces what's called the Fontana circulation, which I'll talk about in the last slide. So this first procedure it requires cardiac arrest, open heart surgery, etc. So at Sick Kids in Toronto, there was an alternative known as hybrid Norwood, which was invented, where instead of performing this reconstructive surgery right after birth, instead a stent is introduced in this connection between the pulmonary and the systemic circulation that we all have when we're born, which later becomes a ligament. And that stent is meant to keep that open, that connection called the ductus arteriosus open. As a consequence of that stenting and maintaining blood flow both to the lungs and systemic circulation, banding is required of the pulmonary arteries because we have a low pressure system in the lungs, a high pressure system in the systemic circulation. And if we have parallel flow, then all the flow will go to the lungs. So these are banded. And later on, certain patients reveal stenosis in the distal arch. So stenosis is a narrowing of a vessel. And the problem with that is that flow is to make its way retrograde along the aorta and reach the coronary bed to alimент the heart. So in case of stenosis, a shunt is introduced between the pulmonary trunk and the innominate artery, so blood will make its way across and then back down to the coronaries. And it's that circulation that was of interest. There are various types of shunts that can be used, 3.5, 4 millimeter shunts typically. These are made out of Gore-Tex. And the fluid mechanics, or the hemodynamics to be more precise, because we're looking at blood, of that circulation was of interest, obviously, to the community, and the American Heart Association supported us to look at that problem. So what we carried out was a research program employing what's called multiscale analysis. So we focus in 3 dimensions and in time-dependent analysis using computational fluid dynamics in the flow field in the region of interest, and in the periphery, which drives the flow field, we utilize an electric circuit analogy of the peripheral circulation. So we have 0-dimensional model connected to a time-dependent 3-dimensional detailed model of the circulation of interest. And so we utilize computational fluid dynamics, which solves the conservation of momentum and mass equations numerically, and connect and tie that into the circuit. And the circuit uses standard elements of resistance for pressure drop, capacitance to account for the compliance of the vessel, inertance to account for the inertial acceleration, and valves in the heart are modeled as diodes. And all of this is driven by time-dependent capacitance or elastance 1 over the capacitance, which drives the flow and provides appropriate waveforms to model the circulation. And so we can extract the geometry from patients, from CT scans using medical segmentation. So these are models that have been extracted from a patient, the identified CT scan, or we can build synthetic models and then introduce stenosis and carry out these what-if scenarios to better understand the flow field. And the outcome of this study was that we demonstrated that all 3 shunts, all these 3 size shunts, will restore the flow back to normal. So these are the waveforms that are driving our system, our interactive system. So this is a coronary waveform. And so that was a useful result. But we also were able to look at the detail of the flow field in these shunts and examine a variety of parameters such as wall shear stress, oscillatory shear indices, vortex formation, stasis in the flow field, to make a recommendation, or at least a statement with regards to the behavior of these 3 shunts when they're placed prophylactically. So if you place a shunt without stenosis in the distal arch, does that create a problem? Are they potentially problematic? And there were some issues with this particular surgery, because if this shunt thromboses, blood clot will make its way directly to the flow is directed to the great vessels, and will make its way to the carotid artery, and so a patient may suffer from stroke, and this is not a desirable outcome. So of all of these, looking at the various details of the flow field, we came to the conclusion, at least in our study, that 3.5 millimeter shunt was the most favorable. And it turned out that sick kids in Toronto had adopted a 3.5 millimeter shunt independently, although we were communicating with them in this study, and so they were happy to see that there was some physics validation behind their judgment, beyond the medical judgment that they had made, and we were very happy also to see such a thing. The other project, which uses similar types of techniques and is currently funded by the American Heart Association, is investigating surgical implantation of the outflow graft of ventricular assist device, which is a pump that's utilized to provide blood to the systemic circulation in case of heart failure. So patients that are awaiting heart transplantations are fitted with this pump, which may be either pulsatile or nowadays continuous flow. And the problem is that this is despite all the advances in material science, and despite all the advances in designing the fluid mechanics of these pumps, they will clot, they will form clots. And these clots will make their way along the circulation to the great vessels, along the vertebral arteries and carotid arteries, and cause stroke. And that's a continuous problem, and this continues to be a problem which plagues these devices when they're implanted for 6 months to a year. So the idea here was to tailor this implantation and try to redirect the thrombi away from the great vessels. All right, and so we are undertaking a computational fluid dynamics study, coupled again multi-scale. If we're doing pulsatile analysis, so this is an example of the flow field that we're rendering through the VAD conduit, and you can see here that there's some native residual flow emanating from the ascending aorta. So we can capture the detailed interaction between the jet and the antigrade flow along the aortic arch. We release particles numerically at the inlet plane of the outflow graft, and we trace these with a Lagrangian particle tracking. We can do this with synthetic models such as this, or we can also extract, there's a workflow, extract the geometry and then modify it accordingly for the study. And we showed that a series of publications that depending on how you orient this cannula, there may be up to a 50% change in the possibility of stroke. So we can reduce, we can't eliminate, but we can certainly reduce the event of stroke by properly tailoring the outflow cannula. This was done in the mean, so in steady flow, and this current grant is looking at pulsatility. So due to the interaction of the jets in such a case, so we've got a 4-to-1 flow split. The cannula needs to be, well, at least to minimize stroke risk, needs to be implanted in a manner that is a little bit more severe than what a steady flow configuration would have been. So depending on the level of support that the VAD is providing relative to the native circulation, a steady flow may be more appropriate, or a pulsatile flow analysis may be more appropriate to suggest the way that such a cannula may be implanted. And that's the subject in a nutshell of that particular research. And the last of the projects that I'd like to go over and do so relatively briefly, because I'm probably out of time, is the last of these reconstructive staged reconstructive surgeries, which is called the Fontana Circulation. So in the Fontana Circulation, the right ventricle is pumping blood to the systemic circulation, and there's a passive return to the pulmonary arteries, to the lungs, through the inferior and superior vena cava. There is a Gore-Tex conduit here that is employed called the Fontana conduit after Francis Fontana, which allows what is called an extracardiac Fontana conduit, so outside of the right atrium, provides return flow to the pulmonary arteries. And the issue with this circulation is that later on in life and post-Fontana, because the only thing that drives the flow back to the lungs is the pressure difference between the pulmonary bed and the right atrium, or right outside of the right atrium and the new aorta and the ascending aorta. There is no assist of the right ventricle. Sorry, the right ventricle. There is no assist of the right ventricle in providing return pulmonary blood to the pulmonary circulation. And so these patients suffer from elevated pressure in the vena cava. And that is problematic. It manifests itself in a variety of deleterious conditions, such as liver cirrhosis, protein loss enteropathy, etc. So there is a group of researchers throughout the world that are trying to energize, come up with means of energizing this circulation. VADs have been proposed, but they have their own problems, which we've seen here with clotting, also a driveline infection, etc. And so we propose to utilize the reserve power of the heart by employing what's called an injection jet. So we have a shunt from the ascending aorta, so the right ventricle is pumping to the ascending aorta, and we extract blood and inject it at high speed in the along the Fontana conduit. And the idea here is to energize the flow, speed entrain it, and therefore drop the pressure and achieve a viable Fontana circulation. We are doing this. We've been involved in this work for several years. We partnered with CHOP, Children's Hospital of Philadelphia, in the first phase of this analysis. This is a patient's Fontana geometry that was extracted from a CT scan. And we looked at these kind of bifurcated injection jet, and finally we've come up with a viable, what we think is a viable combination of a jet and an enlarged fenestration. So fenestration is a return. It's an opening that allows extraction of blood, and we return that blood to the right atrium. And typically these Fontanes have a natural fenestration. So you see this little conduit here. So there's an opening between the Fontana conduit and the right atrium. And the aim of these in current implementations is to try to reduce IVC pressure and inferior vena cava pressure. So there's a very intricate fluid mechanics interaction between a pulsatile jet that is entraining a co-flow, which is essentially non-pulsatile. There is a transient turbulent flow that occurs because of the high speed during systole. So this is the part of the cardiac cycle where the heart is ejecting to the systemic circulation. And so we've utilized large eddy simulation to capture the physics. We control the cardiac output, not to overload the heart. There are some clinical limitations on how much this jet can provide flow to the Fontana. So we respect all of these clinical limitations, and we were I believe on the path. We've achieved a 3.2 millimeter of mercury pressure reduction in the IVC, which is
1 minute left.
Yep, which is a clinically relevant pressure drop, and we're on the way to improve this. And there's a foundation dedicated purely to this Fontana problem, which has picked up this project, and we're looking forward to working on it in the coming years. So in the future, we're looking to take this injection jet work on the Fontana to the next step, incorporate some of our work in RBF, radial basis function train, proper orthogonal decomposition for automatic optimization. We're looking to expand our collaboration with Arnold Palmer and other groups that we're in contact with that carry out this work throughout the world. We're very interested in continuing our meshless methods work, and in particular porting it to these kind of multi-scale hemodynamics problem. We've been using a commercial software, and we would like to develop our own in-house. And then finally, I'm working on the Ph.D. program for the biomedical engineering program, and we're looking to have that in place in the start of the fall of 2022. So we've got to push to make that happen in the College of Engineering and Computer Science. And I'll stop here. I think I've gone way over my time, and I'll be happy to answer questions.